Hello.
Lou.
You are the host now. I got through more material in lecture this afternoon, so you could probably proceed through the lab a little quicker than this morning's version.
Okay. Sounds good.
I'm going to mute myself and turn off my video, and just as usual, when you get done, hang up at the end, it'll auto record.
Sounds good.
All righty.
All right, I'll wait a couple more minutes before we get started. All right. So last time we were dealing with two sets of numbers. We called set 1 and set 2. And we did a bunch of stuff and decided that the normal distribution was a good fit for both. We basically just kind of plotted them and showed some histograms and some charts, and then visually said whether it was good enough or not. We never actually tested in any numerical way whether that was correct. Well, now that's what we're going to do. So let's reload all the stuff we need. Nothing here is new. We're just getting the data from our CSV. We got a set 1 and set 2, and we're getting the mean and standard deviation for both. Additionally, we're going to plot them exactly what we did last time. You can see if I run this again, they will slightly change just like we had before. The red and the green are the original data, and the blue and the orange are the randomized sets. Also, we had the box plots. I think the bar graph is a little more, well, I guess histogram is a little more visible or useful. But now we're going to start actually running a hypothesis test to confirm whether or not we have a normal distribution model. So the first question is, how does the hypothesis test work? Well, it only ever works with something that can be true or false. And that thing that is going to be true or false is called the null hypothesis. I'm going to call it, well, I'll just type the whole thing out. So here we're going to say we fail to reject the null hypothesis. And here we're going to say we reject null hypothesis. Okay. So someone tell me what our null hypothesis is for this first test. We're running the normality test for set 1. What is our null hypothesis for this this example? Remember that our null hypothesis can only ever be something that can be shown to be true or false. So for example, I've got a coin, and I'm going to flip it 1,000 times, and it should be 50-50 whether or not it's heads or tails. If I wanted to decide whether it's a fair coin, meaning that it is close to 50-50, then my null hypothesis would be this is a fair coin. So for what we have here, we have a test that tells us whether something is normal or not. It's called the Shapiro-Wilk test. So in this case, what is our null hypothesis? Yeah, the question is, for this test we're running here, we have a null hypothesis. Now, every time you have a null hypothesis, it has to be something that is true, can be true or false. So it can't be what is the value of X when it can be like 0 to 10. But my coin is fair can be a valid null hypothesis because it's either fair or it's not. But for this example, we're running a test on set 1, and that test is called the Shapiro-Wilk normality test. So what is the null hypothesis for this part? Does it follow the normality test? Not quite. What would the normality test tell us? It's close. So if I run the test on something, what would the outputs of the test be? What are the possible outputs? Well, let's return to the coin example. Let's say I have a test that can tell me whether the coin is fair or it's not fair. So what are the possible outcomes of that test? Yes, that's it. So normal or not normal. So the null hypothesis here is set one is normal. That's our null hypothesis. So if we fail to reject it, what that means is we have inferred that set one is normal. If we do reject it, we've inferred that set one is not normal. So let's run it and see what happens. All right, we fail to reject. So this should come as no surprise based on how set one looks, that set one appears to be normal. Let's do the same thing for set two. We get the same thing. So the Gaussian distribution is the normal distribution. Gauss was the one who discovered it, so it's named after Gauss, but it is also called the normal distribution. So what our test does is given our set and a confidence of 95%. This is 95% because 1 minus 0.05 is 0.95. So with a confidence of 95%, we can say that set two is probably Gaussian, probably normal. Okay. So that's pretty simple. Let's check something else out. I have another test, and what this test says, given two sets, do I believe they are from the same distribution? So I'm running this on set one and set one S, where set one S is randomly generated from the same mean and the same standard deviation. So if I have a test that tells me if the two inputs are probably from the same distribution, what is the null hypothesis for this case? Someone other than Chris, because Chris has been a trooper. There are some questions at the end, and there's the homework. And we're only going to get to those if we can actually get through this in the next 48 minutes. They're not hard, but neither is what I'm asking here. It's just asking for a little bit of participation. Yeah, sure. The question is, here, the null hypothesis that we're trying to test is set one is normal. So it's either normal or not. So if we reject the null hypothesis, I'm sorry, if we fail to reject, we're going with that it's normal. If we reject it, we're saying it's not normal. Same thing for set two. Now the question is, what's the null hypothesis here? I've got a test that, given two sets, tells me if they're from the same distribution. So I'm using that test on set one and set one S. So what's my null hypothesis? Yeah, the null hypothesis is set 1 and set 1s are from the same distribution. So if I fail to reject it, then we're saying that with 95% confidence that they're from the same distribution. All right, let's check it out. Well, we fail to reject, which means with 95% confidence, I can say set 1 and set 1s are from the same distribution. This should come as no surprise. 1, they look very similar. And 2, we took the exact mean and the exact standard deviation from set 1 in order to make set 1s. So I would be pretty shocked if they weren't from the same distribution. We do the same thing for set 2 and set 2s. So here we say probably the same distribution with a 95% confidence. Now, the question is, do we think set 1 and set 2 come from the same distribution? So if we look here, set 1 blue, set 1 green, and set 1s blue, we've determined that these are probably from the same distribution. No shock. Same thing with the red and the orange. Now, do we think that the green set 1 and the red set 2 are from the same distribution? Just visually? They both might be normal, but they're pretty far apart. I agree. I think no. So if this were to say that set 1 and set 2 are from the same distribution, I'd be really surprised. So we have rejected the null hypothesis here. The null hypothesis is that they are from the same distribution. So we don't think they're from the same one. Similarly, set 1s and set 2s will get the same result. So we can say that at a 95% confidence level, that set 1 and set 2 are different. Seems pretty intuitive, seeing as how different they look. Can also use the bar graph or the box plot if we prefer. Okay. Any questions before we move on to the next example? Okay. We've got another set of data. And in this data, we've got some recorded stuff about students. And the thing we're interested in are the scores they got on math, reading, and writing. So first things first, let's get our CSV in. Let's make a data frame out of it. And every time you make a data frame like this, it's usually useful to use the describe method. What will this do? Well, it tells me there's 1,000 students, and I get the mean of all of their scores. Now, it is worth repeating. Our hypothesis here, our null hypothesis is there is no difference in the means of student performance in math, reading, or writing. So I look here and I see that we've got a mean of 66, 69, and 68. Are those close enough to each other? I don't know. If our range is negative 1,000 to 1,000, 66 and 69 are pretty close. If our range is 60 to 70, no, I don't think they're very close. So the question is, are they close enough? Well, we can use our eyeballs. And don't worry about these warnings. It just says warning. It's not actually an error. We can use our eyeballs here. We've got a green bar, which is writing. And we got an orange bar, which is reading. And we got a blue bar, which is math. I'm pretty confident visually that the green and the orange are pretty close, but I don't think that the blue one is very close. Well, I would say it's close. It's different enough to say that they're statistically different. The range is 0 to 100. So a distance between the means here of not a whole lot actually ends up being different. So let's, instead of just trying to visualize, let's actually use our tests that we've been using. So we're going to use the same test that says whether two sets are similar or not. So if we fail to reject, then we're saying they're probably the same distribution. If we do reject, we're saying they're probably different. And we're comparing math, which is blue, and reading, which is orange. So what do we think is going to happen? Are they going to be the same or are they going to be different? Can't run these cells? Okay. Well, I can attempt to fix that. You need the actual CSV in order to run it. Which is interesting. Actually, here's what I'll do. We'll go to where the actual lab is. This might be the wrong one. Oh, that was useful. We'll go to lab 22. Okay. Now here's where the lab is, and you see the CSV isn't actually here. Well, if we go to the web root, oops, one too many. You can see that the data is right here. So I'll copy the link for this and give it to you. What that means is the information needed to get the actual data is in the recording. So that means I don't have to answer emails about it. Okay. So that should fix your problem on getting the data frame to actually run. You should be able to import it now, as long as you bring it into your bay. Okay, so we have a test that will tell us at a 95% confidence if two things are from the same distribution. So just based on visually, I'm going to say that 1 and 2 are different, but 2 and 3 are similar. So let's run it and find out. Sure enough, 1 and 2 are different. Let's try 1 and 3. So if I'm correct in assuming that 1 and 2 are different and that 2 and 3 are similar, then I should be able to say that 1 and 3 are different. Oops. And again, probably different distributions. Well, that leaves 2 and 3. Do I think that 2 and 3 are different? No, I think they're pretty close. So let's find out. Okay, we can say with a 95% confidence that set 2 and set 3, which is reading and writing, the orange and the green, are probably from the same distribution. Cool. The last test we're going to look at in this example, it takes any number of tests you want. In this case, we're going to give it 3, and what it does is it tells you, is every set you've given me from the same distribution? So we should already know the answer to this. The question is set 1, 2, and 3, which is math, reading, and writing, are all 3 of those from the same distribution? The answer is already here. So what's the answer? Are they from the same distribution or not? No, they wouldn't be, because we already know that 1 and 2 are different. So just knowing that, we can say that 1, 2, and 3 are not from the same distribution. Let's run it just to be sure. There we go. Probably different. Now, why does it say probably? Well, it's because in statistics, unless you're looking at the same thing, so set 1 or set 2 and set 2, this is the only time you can ever say 100% set 2 and set 2 are the same thing. Of course, they're the same thing. They're the same thing. Any other time, you can't really say that you are 100% confident about anything, really. The standard is this p-value of 0.05. This means 95% confidence. That's the standard. It works pretty well, and it doesn't take a whole lot of computation time. Okay, so that's the second example, which will be in homework. It's running 2 different tests, one we've seen before and a new one. So any questions on that before we look at the last example? Can you repeat the last bit? Yeah, I was just saying that in this example, we did 2 different tests. The Mann-Whitney test, it's not important that you know what it is, but it's comparing 2 things to see if they're from the same distribution. And we also ran the Kruskal test, which will run, in this case, 3 things to see if they're all 3 from the same. And I think I said it's not important that you really know what the names are, just how to use them and stuff like that. Okay, let's look at the next example. I have a task of figuring out whether or not I need to change a button on my website. I want to increase sales because, you know, I want to make more money. And it may make more people buy stuff if I make the button look nicer. But I don't know which one's better, the old one or the new one. So what I'm going to do is I'm going to set up a bunch of people and give some of them the old button, some of them the new button. And I'm going to see whether I see any change in the number of sales. Now, if I see 1 change out of 1,000, is that enough? No, not really. If I see 50% more, yeah, that's definitely enough. But where's the line? Well, we can run the same test we've been doing with this example. So this is called an A/B test. It's used interchangeably with split testing. And what we're going to do is we're going to have 1,000 users. We're going to put 550 onto site A, which has the old button, and 450 on site B, which has the new button. Okay, so we actually did that. Well, not us, but for the sake of argument, we did that. We say 550 went to A and 48 users made a purchase. 450 went to B and 56 made a purchase. Is this a statistically significant result? I don't know. It appears that I have a rate of like 9% of purchase on site A. And I have about a 12% purchase rate on site B. Is that enough of a increase in sales in order for me to spend the money and all the time and effort to change it from button A to button B? That's the question. So how do we figure that out? Well, let's turn to some statistics, shall we? There's only 2 options. You can either click a button or you can not click it. That's the only things you can do. They can either buy something or not. There's no marking whether they bought too many things or less things. It's just, did they buy something? So that gets us into what is called a binomial distribution. And you'll see why it's called that here in a second. So this is all the stuff we had as our data. We're plugging in probability of A with the rate we have here for site A, rate B, site here. So it's just using the variables we have before. And this is what we get out of it. And this is why it's called a binomial distribution, because there are 2 of these normal looking distributions here. So question is, which one's better? It can be a little bit misleading because it is possible that there are parts of A that are greater than parts of B. For instance, there are instances of A where you made 60 sales, and it's possible that in B you made 45 sales, which would mean that you're wasting your money. So since we're interested in the average number of sales, let's try approximating this with a normal distribution instead of a binomial one. One more thing this will let us do is, you notice how we had not an even number. We had 550 here and 450 here. Well, we can account for that. So what I have here is, instead of number of sales, what I have is the purchase rate. And this purchase rate, as you can see, lines up exactly with the rates we calculated here. So for site A, we have the mean purchase rate at like 8%, 9%, something like that. And this is regardless of how many people there are. And for site B, we have our purchase rate something like 12.5%, regardless of how many people there are. Because this is normalized, we don't actually care about how many people were in each group, as long as it's not like 2 people in set A. You don't. It's not big enough for a sample size. So that gets rid of 2 problems. The last question we have is the difference between site A and site B, the change we see, is it significant? I don't know. But luckily, we have some tests that let us do that. So we're going to utilize the fact that the sum of normally distributed random numbers is also normal. What does that mean? Well, you know, normal distribution looks like this. Well, the nice thing here, I have 2 normal distributions. There's a fact, which you're not expected to prove or anything, this isn't a math class, that the sum of 2 normal distributions is also normal. The difference is also normal. So we're going to abuse that fact. So what we're going to do is take the sum, or maybe the, which one is it? We're going to take the difference of, was that a question? No, I just think it's an open mic. Okay. So here is what we have. We're showing here, PDF stands for partial, probability density function. That's what it stands for. Not that you really need to know what that is, but you can see the probability that B is greater than A falls into most of the area here. If the area were 1.0, that would mean it is impossible for the old site to ever be any better than the new site. So we're interested in finding out how many times is the new site better than the old site. Well, if the curves looked like this, if they look like this, so here's the old site and here's the new site, notice that there's no overlap at all. So that means that every single case here is less than every single case here, even the outliers. But that's not what we have. What we have is there's a little bit of overlap right here. So the question is, how often is this overlap? Well, I don't know. It's kind of hard to say just by looking at it. If I were just looking at it, like the entire width of everything is kind of like that. And this width of this is like maybe a fifth of it, maybe a fourth of it. I don't know. It's a little harder to calculate visually. I would have to guess maybe like 80%, maybe. But if we run our test, what actually turns out is 97% of the time. 97% of the time, we have a better purchase rate. So we do have evidence that B is better than A. Now, we've done a lot of stuff to try and explain the concept. So we've gone from this binomial distribution to doing the double normal distribution to do a single one. But this is all so that you can hopefully understand a little bit about what's going on so you're not confused. All of this can be done in a super simple test right here. Here is just using our original data. We have a confidence at this rate that our B is going to be greater than A. And we can also use the test we used above to figure out whether our new site's going to be better or not. So if we use the test we used in the previous example, we can say with a confidence of what, 97.2%. So I am 97.2% confident that the results on my B is going to be better than my results on our A. So a bunch of explanation here, which can be summarized in just one block of code. Take the rates and compare them to see which one is likely to be better. Okay, that's everything. There is a question down here, and I already answered it above when we were doing the Kruskal test, and I did that on purpose so that if you were paying attention, this will be really easy. Okay, so before I look at the homework, which, as you won't be surprised, is everything we've already done, just with some different data. Are there any questions before I move on to the homework? All right, well, let's look at the homework then. Okay, we've got the same data we had last time. In fact, I'll just pull it up. Here's last time. Get our lists into a data frame, easy peasy. Describe the lists data frame. There is literally a method you can run that will get you everything you need in order to do that. Granted, this is, don't just run it. That's not you're supposed to put this into English and then make some histogram. After that, interpret what you have, use some English. Okay, what's different? Wow, we had like 3 people show up. Oh, no, there's duplicate people. Interesting. What's different? Well, we've got all the stuff we had before, but now we have to actually do a hypothesis test. So our test is going to be testing a null hypothesis. And what is the null hypothesis? It's right here. Are the means of our 2 pieces of data here, 2 sets, the same? Are they similar enough? The real question is, are they statistically different? Significantly different, sorry. That's the question. And you can use your either your t-test or your Mann-Whitney test, and you have to figure out which one. And it's said right here, the conditions on which one to use. And then again, explain in English what you got. Okay, that's pretty much it. In fact, that's not pretty much it, that is it. So, any questions? anything at all? How's my day? It's extremely windy. There's dirt everywhere. Might be calming down. But yeah, I could even taste the dirt. Alrighty then. Well, good luck on the homework, and you know where to find me.